I'm going to talk to you today a little bit about our view at Cerebras of the power of wafer scale computing for extreme scale AI and HPC. By way of background, I'm a researcher myself by background, undergraduate and graduate work in physics for signal processing. Came into deep learning as a method to extract structured data from unstructured data sets. And so I see that there is a tremendous potential for AI and HPC methods for scientific research at very large scale. But in some sense, we as a community are constrained by compute today. Traditional architectures, as you've heard from our previous speakers, are not optimal for many tasks that we face today in AI and HPC. And at Cerebras, we've taken a unique approach to solving that compute problem to put extreme scale compute resources into the hands of more organizations for this kind of work. So I'll first set up this discussion with a little bit of an observation about the challenge and opportunity. And we've seen similar charts earlier today. But there has been a massive, an exponential growth in AI compute requirements recently. Looking just at the natural language processing space in deep learning, we see over the course of 2 years between 2020 and 2022, a 3 order of magnitude growth in compute requirements for large state-of-the-art AI models. 1800x compute difference between GPT-3, introduced by OpenAI, and BERT Base, introduced by a team at Google in just 2 years. And we don't see this trend waning at all, and I'm sure you don't either. We expect trillion and multi-trillion parameter models around the corner. And indeed, traditional approaches to clustering together general purpose processors has advanced the field quite a bit over the past decade or two. But it's starting to reach its limits for large-scale AI, as shown in the chart here. This is some work published in 2021 based on earlier ML-perf results, but it shows a trend that's common across many large-scale AI tasks, which is that as you build larger and larger clusters, indeed training time goes down, but that scaling is far from linear. So as this chart shows, for example, you would need approximately 500 chips in a cluster just to see your time to convergence accelerate by 100x or 160x. Right? So we really need a new compute solution for these large-scale AI and HPC problems. Just to go a little bit further, the sort of limits of existing scale-out approaches is that, particularly at this very large scale, these workloads need not only massive compute, but as we heard earlier today, also massive communication bandwidth for layer-to-layer communications in complex topologies of large neural networks, and massive memory bandwidth so that your compute can quickly access weights and activations in your model. And particularly as models and layers get very, very large, these models can no longer fit on individual processors. And so you can, at some point, not scale in an only data parallel way anymore, but you have to scale in a model parallel way and sometimes a tensor parallel way. And you have to develop a distributed implementation of your large-scale AI workload that's unique to that neural network topology and unique to that cluster, which is possible, but effectively slows down your ability to iterate and experiment with these large-scale models. So these factors of compute, memory bandwidth, and communication bandwidth all get intertwined in these large-scale distribution problems, and that complexity scales dramatically as the problem size and cluster size increases. So at Cerebras, we've taken a slightly different view and are building a much larger scale foundational node that not only delivers more performance in a single node than a traditional cluster or multiprocessor system, but that can be clustered together more easily to achieve extraordinary scale with a simple programming model. We were founded in 2016. We're on a mission to not just change this landscape and accelerate research by a little bit, but by a lot. We now have over 400 engineers in hardware, software, and machine learning research. We've got offices in our founding Bay Area in California, but also San Diego, Toronto, Bangalore, and we have a growing body of enterprise customers, both in government and commercial, around the world. Okay, so let me speak now a little bit about the architecture of our solution. The heart of our machine, that many of you may have seen before, is a revolutionary processor that we call the wafer scale engine. This is what it looks like for scale. That is a real full-size person in the picture. This is an unbroken 8.5 by 8.5 inch piece of silicon with 850,000 individually programmable compute elements on that one piece of silicon. In addition to those 850,000 cores, by the way, all of which have a general purpose instruction set and a set of extensions to handle sparse tensor-based linear algebra operations at full utilization. All those cores are additionally interconnected over silicon in a high bandwidth, low latency 2D mesh on the chip. And the data flow traffic pattern between cores and across the entire wafer is fully configurable in software. So we can support arbitrary network topologies and communication topologies, run different programs on all 850,000 cores if you really wanted to. And then last but not least, we also have 40 gigabytes of all on-chip SRAM. Think of this as uniformly distributed, about 48 kilobytes of memory per core across the entire wafer. So all of that is immediately accessible in one clock cycle from its associated core. So in a nutshell, this is a 850,000 core sparse linear algebra accelerator all on one chip. This just illustrates the physical scale of the wafer scale engine on the left compared to the largest state-of-the-art GPU on the market on the right. But the point here is not just to show the physical scale, but that by bringing all the compute and memory and communication resources together on one wafer, we not only deliver approximately 2 orders of magnitude more cores, but 3 orders of magnitude more on-chip memory, and 4 orders of magnitude more core-to-core communication bandwidth and memory bandwidth than you could achieve on the processor at the right. Once we arrived on that large-scale wafer architecture as the right engine to power our customers' deep learning and HPC work, we then had to completely rethink the system design to package, power, cool, deliver data to that high-performance engine. And for that, we had to be more than just a chip company, because we weren't going to be able to slip that into a desktop machine or even a 1U standard rack mount server. So we had to be a systems and full solution company at Cerebras as well. So we built the server that's shown in the bottom of the rack here. We call this the CS2. This is our flagship product. It is what we are building and delivering to customers today. It is what exists at ANL in ALCF, for example. And each one of these systems typically delivers the performance of many tens to hundreds of GPUs, depending on the task. And we've built this machine to easily deploy into standard racks, as shown here, and connect over standard power and standard interconnect to adjacent infrastructure in your cluster so that it's easy to deploy and operate and maintain. Just to double click and take a look inside, this is an exploded view of that CS2 server. And what you can see is in the top right, back there in the back, I can't even reach it, but in the top right is what we call the engine block. And that's where the wafer scale engine is actually mounted vertically in a sandwich with power delivery in the front and cooling in the back. And what you're looking at on the right side of that engine block in the brass is a custom engineered liquid cooling manifold that drives cold water across the back of that dinner plate sized processor and brings warm water back around and circulates it down to the bottom of the chassis, where you can see a heat exchanger lives there. Our primary systems are built to be facility water cooled then at the edge. So we bring facility water to the back of the machine, then have a water-water heat exchanger that cools the closed internal loop. And we are also building an air-cooled system that leverages these same components so that we can reach a broader audience and go into even more data center environments at a broader range of conditions. But we had to build this entire machine to really leverage the full potential of that wafer scale processor. So that's the chip and the system. But as data scientists, ML researchers, HPC users, right, you're probably asking, that's all great, but how do I actually program this machine? And for that, we built the software stack shown here. The short answer is that for deep learning work, you program the machine with standard ML frameworks. We support TensorFlow and PyTorch today. For many HPC applications or to develop custom computational kernels, we also have a lower level software development kit that includes a C-like programming language so you can roll your own kernels and then have those called back by the stack. Whether you are using a kernel that our team has written or you've written, what happens is your workload, say your training or inference program, is translated at the top of our stack into an intermediate representation that we call Cerebras internal representation high level. We have a lot of engineers and not too many people thinking about good marketing names for internal ML representations. So we call this CER-H. This intermediate representation then broadcasts to the downstream components of our compiler the compute operations and the communication pathways for your workload. And then our compiler identifies compute kernels and communication routing and basically lays out your network all on our wafer on one or more machines and translates that network of operations and communication pattern into a set of computational kernels and communication configuration to operate on the wafer. The real advantage of this is that it gives you as a user access to effectively a cluster scale compute resource, except you don't have to use distributed version of framework. You don't have to think about OpenMPI or Horovod. You're just getting access to all of that horsepower, but effectively with the programming paradigm of a single node. So just to illustrate this for the TensorFlow case, this is what it looks to set up and run a training job. And you're basically just going to import Cerebras estimator. So for TensorFlow, we actually use the estimator API and compile down through TensorFlow's accelerated linear algebra, or XLA library. It's the same pathway that you might use to program a TPU. So you import our estimator and run config, and then you use exactly the same semantics as you would for standard TensorFlow to define your model function, your input function, and instantiate estimator. Define your configuration here, point the config at the IP address for that single big CS node, and then you are off to the races. We use Slurm, and our customers use Slurm to orchestrate this as a part of their clusters and also queue up jobs. So in a sense, you can think of this as a very high performance network attached accelerator that you would program just like any other device. So let's transition a little bit from architecture and programming into value and use cases, right? Earlier I mentioned things like tens to hundreds of GPUs and ease of programming in a single node. And I think at the end of the day, from the research standpoint, performance should translate into accelerated time to solution and more iterative ability to execute more experiments per unit time. Right? I should be able to test more hypotheses per unit time and effectively thereby decrease the cost to insight or new application development. So I'm going to talk to you today about a few example use cases that span the spectrum of, I'll call it pure AI or deep learning, to pure HPC, to a few interesting use cases of our machine for interesting AI use cases at the convergence of AI and HPC. But before I provide examples of say, benchmarks and customer use cases, I think it's just nice to not hear from me, but hear from our actual users. So we've been fortunate to partner with leading enterprise organizations, both in government and commercial, for exciting scientific applications ranging from, of course, Argonne National Labs, where models like UNO is training hundreds of times faster on Cerebras than it is on traditional GPU, to commercial leaders in biomedical, life sciences, and pharmaceutical development like AstraZeneca and GlaxoSmithKline. At AstraZeneca, they're training large language models in a matter of days that used to take them weeks on their multi-GPU systems. At GSK, they're actually building new models that they weren't able to experiment or build before because now they can test more ideas per unit time. And at TotalEnergies, they're accelerating some of their fundamental physics-based modeling and simulation to drive more insight more quickly into their clean energy research. The example at GSK is actually a pretty cool one and is in that camp of pure deep learning. So many of you may be familiar with the BERT-based models, and now there's sort of an extended family of large BERT-based models for language modeling. There's also BERT-based models that model the behavior of DNA sequences. That's called DNA BERT. So the researchers at GSK started with that DNA-based BERT model to develop some new genetic medicines. But they wanted to train it not just on DNA data, but also epigenomic data on things like transcription factor effectiveness and targeting. On our machine, they built and trained this model in 2.5 days, and it would have taken them about 24 days on their 16 GPU setup. So not only did we deliver 10x faster training than a 16 GPU setup, but my favorite thing about this is the quote on the bottom, which you can also find in their archive publication, but that this training speed up, it's not just about performance, right? It's about allowing them to explore architecture variations that would have been prohibitively time and resource intensive on a GPU cluster, right? If every experiment takes you 24 days, you're going to have a long graduate or postdoctoral career before you find the right network architecture to deliver the right accuracy for your results. But if you can do it in 2.5, you're in business. The story extends into the pure HPC space. I mentioned TotalEnergies earlier. They're using our machine in part, in addition to some of their ML workloads, to accelerate seismic data processing using a finite differences method. And on our machine, they were able to achieve more than 200x speed up on that finite differences routine for seismic data processing compared to an A100 GPU. So for them, this is really just scratching the surface, but allows them to iterate much more quickly on their modeling and simulation routines. Another cool one, once again in the HPC domain, is there's a group part of the Department of Energy, the National Energy Technology Laboratory, that's using our machine to accelerate stencil code-based processing for computational fluid dynamics. The team there, using our lower level software development kit and custom kernel development languages, implemented a method for biconjugate gradient descent for this computational fluid dynamics routine, and actually achieved 200 times better performance on one Cerebras system than on the entire Joule supercomputer. And this particular capability, handling, say, sparse stencil-based codes for HPC, as well as deep learning, is powered by our system's ability to operate at all BLAS levels at full utilization. We've talked a couple of times about this from some of our earlier presenters, so I won't rehash the wheel too much, but you can think of our big 850,000 core processor. Each one of those processing elements is a fine-grained data flow engine that can operate at BLAS 1 at full utilization because of its memory bandwidth and access to that on-chip SRAM. And so that kind of capability not only allows us to accelerate deep learning, but also gives us staggering performance on these kinds of applications. Closing up on the use cases, a couple of cool ones at the intersection between AI and HPC. For me, this is a really, really exciting area that we've started to see blossom, I think, just over the past couple of years. But at Lawrence Livermore, back in my home state of California, we deployed a Cerebras machine and have integrated that over the network with the Lassen supercomputer at Livermore. And we're using the two together, doing high-performance computing, physics-based simulations on Lassen, pumping the output from those expensive, high-precision computations to our machine, which is running an autoencoder deep neural network in inference, and then piping the result back to Lassen to inform the next step in that exquisite physics simulation. This was really a first of its kind deployment, a heterogeneous cluster built for the purpose of what they call cognitive simulation, that is AI-informed physics-based simulations, and it's running today and getting faster all the time. We also did some really cool work that I'm proud of. Last year resulted in the submission of 2 Gordon Bell Special Prizes for COVID-19 research with our partners at Argonne National Labs. One of them was selected as a finalist, but both were involved in using our system next to the Theta GPU cluster at Argonne, once again, to accelerate physics-based simulation. In this case, it was molecular dynamics simulations related to COVID-19 research, and use our machine as a counterpart to that to accelerate training and inference of a large convolutional variational autoencoder. And using our machine, we were able to show about 100x GPU performance from one of our machines out of the box, and once again, getting faster as we optimize the software and implementation together all the time. But collectively, all of these are stories about accelerating time to solution to enable more iterative research at large scale. I would love to talk more about some of the specific use cases and get into it with you. I think you guys have a really exciting week on tap, so I'm happy and proud to be able to be here and introduce Cerebras to you. We are the first wafer scale systems for AI and HPC. Gen 1 was introduced in 2019, Gen 2 was introduced in 2021. We are really just scratching the surface, and we have a multi-year roadmap to go even higher performance and larger scale. Even now, we're delivering orders of magnitude more performance and simple single node programming on our current generation devices. And we recently announced ability to do things like train models like GPT-J at 6 billion and Neo-X at 20 billion on a single machine and deliver linear performance scaling across multiple machines. So this is really just the beginning for us. We're going bigger already. I also want to encourage this group to think big, right? Extreme scale computing is really foundational for iterative science. I heard somebody earlier today mention a golden age of computing. I think that's exactly right. And I expect that it will result in fundamentally new discovery. And I think that's the opportunity that we collectively have and that we at Cerebras really at the end of the day build for. So happy to be here with you. I think you guys have an exciting program ahead. I'd like to encourage you to think big and of course come and find us so that we can go bigger together. On that front, if you're curious to learn more, you can find us online, cerebras.net. We've got system specs, we've got documentation in our new developer portal online under cerebras.net. We've got code examples and a model zoo. And you can, of course, always reach out to us directly for access. And we also have a commercial partnership with a cloud company called Cirascale, so you can get time on systems through them. But particularly for this group, right, we have systems available for scientific research with our partners at ANL. Of course, many of you are familiar with the ALCF program. Our systems are a part of that. We also have systems at NSF-funded facilities, Pittsburgh Supercomputing Center and NCSA here in Illinois. If you happen to be on the other side of the pond, we also have systems at Edinburgh Parallel Computing Center, or formerly known as Edinburgh Parallel Computing Center, EPCC, and also at LRZ in Germany. So I'm happy to answer any questions, and thanks once again for your time.
Thank you. Have any questions?
Okay. So what is going to take to compile a full HPC program, for example, for 0?
Do you mean in terms of development process or just wall clock time? How long does it take to compile the thing?
Just talk about that.
The development process. Okay. Yeah, so you, first of all, you can begin with our SDK. So we have kernel examples, we have a programming language, we have debug tools, we've got documentation. So if you want to run what we've already written, then it's as easy as running that first on a simulator, which runs on a standard x86 CPU machine, and then compile and run through our SDK after you set up the input pipeline on the machine. So it's very straightforward. If you want to develop a fundamentally new computational kernel or communication pattern, then we have guidelines for that, and we can either help you through it or you can find your way through our documentation. But happy to chat more, and if it's a mutually interesting problem, we can certainly partner and co-develop.